All right, so on your problem of the day where we were looking at naming covalent compounds, those are easy to spot. They're between nonmetals. And that's where you share electrons versus ionic bonds. There's a transfer of electrons occurring, so it's between usually a metal and a nonmetal. However, there are polyatomic ions, and we'll talk about those later today or tomorrow. All right, and we looked at ionic bonds as being the strong attraction between a cation with a positive charge and an anion with a negative charge. But they actually have their own unique naming system, and we'll get into that today. But I did want to kind of compare the difference between these. Actually, sorry. And go back to the law of definite proportions. Does anybody remember what the law of definite proportions says? Essentially, the easy thing to remember is it says water is always going to be 2 hydrogens and 1 oxygen in a 2-to-1 ratio, right? So it says the ratio is always defined. So molecules or compounds are made up of a fixed ratio of atoms. And this applies both for covalent and ionic compounds. It's a little bit abstract, but let's take a look at a covalent compound first, the easy example. And the example I told you just a minute ago was that water is always going to be 2 hydrogens bonded to 1 oxygen. Of hydrogen to oxygen. All right, ionic compounds are a bit different. With ionic compounds, we don't have these bonds between atoms, those covalent bonds. Instead, it's an attraction between cations and anions. So let's take an example of table salt, right? Table salt, if you think about it, is a sodium cation that is really attracted to a chloride anion. And it's always going to be a 1-to-1 ratio of sodium to chlorine, or chloride, I should say. All right, so another way of thinking about this is, let's say I have a sodium atom right here. It's going to snuggle up next to a chloride anion right there, and then this will continue on in this big 3-dimensional network where you're essentially making this checkerboard of sodium and chloride anions and cations. Oops. So I'll just really quickly fill out the rest of this. So it is a little bit different. You don't have defined individual molecules floating around in space. Instead, what you have is basically this big brick wall of cations and anions. So it's a 3D network of cations and anions. The important thing to remember with this, though, is it's still a 1-to-1 ratio of sodium and chlorine, so we still represent it as NaCl. We don't write Na infinite and Cl infinite. We want to define the ratio whenever we write out the molecule. So it's still a 1-to-1 ratio of sodium to chlorine. This is referred to as a crystal lattice. It's this really strong brick wall effect of cations and anions kind of stacking together. So if we look at this in a bit more detail, sodium is represented by these blue dots. Sodium's really small compared to chloride. Why do you think that's the case? What do you think?
Sodium has less protons and neutrons.
Yeah, sodium has fewer protons and neutrons. That's one thing. What about the number of electrons? It's got a lot less electrons than chloride. So chloride in this case is the bigger atom. But you see how it's kind of stacking in this big three-dimensional network? And then if you zoom out, you can see a big network that almost looks like a cube. And then if you actually zoom in on salt, like table salt with a microscope, you'll see that it's actually cube-shaped. The crystals really like to pack in this cubic fashion. Does that make sense? It's kind of abstract to think about. All right, so now what we have to do is we have to practice predicting ionic charges, and then we'll get into naming a bit more. So the first thing is remember that main group elements, meaning anything that's not a transition metal, wants to gain or lose electrons to have an octet. Or lose electrons so that they have an octet. All right, and we'll take an example. Go back to sodium and chlorine. We said yesterday that sodium has a valence of 1, chlorine has a valence of 7. However, what you can do is say, all right, the sodium is going to toss its electron over to chlorine. That means that the sodium is +1 because it lost its electron. And then chlorine, because it gained an electron, is going to be -1. But the important thing to remember is during this process, both now have an octet. Okay? So it's pretty easy to remember the charges for ionic compounds. First thing to always remember is group 1A. What do we call these? Alkali metals. They always have a +1 charge across the board. So alkali metals are always +1. Group 2A, these are the alkaline earth metals. They're always going to be +2. Pretty easy to remember. This whole section, the charges can vary, so we're just going to skip that. These are the transition metals. You see down here how iron can be either 2+ or 3+. Copper can either be 1+ or 2+. It's really hard to predict the charge of a transition metal. All right, and then as we go over, group 3A is always +3, pretty easy to remember. So atoms in group 3A would rather give up 3 electrons than try to gain 5 electrons. It's easier to lose 3 than to gain 5, right? When we go to group 4A, we're kind of stuck in the middle. So for group 4A, you've got an option. Do you want to gain 4 electrons or lose 4 electrons? Both options really aren't that good. It takes a lot of energy to gain 4 or to lose 4. So typically, atoms or elements in group 4A aren't ionic because it's really hard to rip off that many electrons or gain that many electrons. All right, then we jump over to 5A. 5A, it's actually easier to gain 3 than to lose 5. So these are normally -3. And then same thing with 6A, it's easier to gain 2 than to lose 6. So it's -2. And then -1 for the halogens. It's a lot easier to gain 1 than to lose 7. All right, noble gases, if you remember, don't need to gain or lose electrons. They already have an octet, so they're never going to be ionic. But it's pretty easy to remember. All right, so I'll show you a few key points about ionic compounds. The first is that charges must cancel out. In an ionic compound. So, for example, we saw with sodium that it was +1 and chloride is -1. These charges cancel out. And when they cancel out, that means we wrote everything correctly, and the overall compound would be represented as NaCl. All right, but it does get trickier with harder compounds. So let's do some practice. What is the salt that forms when potassium reacts with oxygen? With oxygen, here we go. All right, so let's think about it in terms of potassium and oxygen. How many valence electrons does potassium normally have? Just in its neutral state. Don't think about it as even being an ion. 1, okay? Oxygen normally has 6. Whoops, got too many there. So oxygen normally has 6, so we can say, well, potassium can give 1 electron right there, but even then, oxygen only has 7 electrons. So maybe we need 2 potassiums for every 1 oxygen. So then I would say, okay, my second potassium atom can give its electron to this remaining spot. Now when you do this, you've got potassium atom here and here, both lost electrons, so it'd be a +1 charge. And then oxygen now has 2 extra electrons, so what charge should it have? -2. Yeah, -2 or 2-. Just like I said before, all of these charges cancel out. Right, so 2- cancels out with the 2 positives. And so then when we go ahead and try to come up with the formula for this, we'd write K subscript 2 to indicate we've got 2 potassium atoms. And then oxygen. We don't have to do a subscript 1. It's implied, right? So this would be potassium oxide. Pretty easy to do. I'll show you another trick, though. And the trick is to draw out your expected ions. And then do something I called flip-flop. Pretty fancy science term. So I'll show you what I mean. Potassium is in group 1A. We said anytime you have an atom in 1A and it's in an ionic compound, it's going to be +1, right? So I'd say +1 for potassium. And then oxygen is in group 6A. It's a lot easier to gain 2 electrons than to lose 6. So it's normally 2 negative when it's ionic. So what you can do is say, all right, I'm going to take this number, move it down to be the subscript here. And then this number, I'm going to move to this subscript. And so we'd say K2O1. However, like I said, you don't need a subscript 1 really ever. It's implied if you don't have it. So you can just really easily flip these charges and determine the overall molecular formula. Does that make sense? It's a little bit weird, but you've got to remember the overall charge based on what column it's in. The easiest way to do is to kind of pencil it out on your periodic table. +1 is group 1A, +2 is 2A, +3 is 3A, skip 4A, and then 5A is -3, 6A is -2, 7A is -1. All right, so now let's try a harder one. So let's box this off. What is the ionic compound, and I'll just abbreviate compound, that forms between magnesium and nitrogen. So this one's a little bit tricky. But let's think about it, right? We've got magnesium. What charge does magnesium have when it's ionic? 2. It's in group 2A, right? So magnesium is going to be 2 positive. And then nitrogen, if we look at the periodic table, is in group 5A. So what charge would it have? -3. It's easier to gain 3 than to lose 5, right? So nitrogen being in 5A, it's closer to 8. So we'll say 3-. Okay? But now we can use that flip-flop trick, right? So what I'm going to do is take these numbers, flip-flop them. So now I've got magnesium, the subscript 3, and then nitrogen with the subscript 2. So this would be the molecular formula for the compound that forms between magnesium and nitrogen. But let's try to show this pictorially too, because I know it helps. We know we've got 3 magnesiums. So I've got magnesium, has a valence of 2. We've got 3 total magnesium atoms originally with a valence of 2, right? And then we've got nitrogen. We already predicted that we have 2 of them. Nitrogen normally has a valence of 5. All right? So what we can do is say, all right, this magnesium is going to give 1 electron here, 1 electron there, but that nitrogen is still short 1 electron, right? It would only have 7. So maybe it's going to take its last electron from this magnesium, and then this other electron can go to the second nitrogen, along with the 2 electrons off of magnesium. So we can kind of shuttle all those electrons over. But now when we do this, we've got magnesium with the 2 positive charge, specifically 3 of them. And we've got 2 nitrogens, now with a full octet. And each nitrogen took 3 electrons, so it's 3-. And just like I said before, if we think about our cations, the net charge for all of these is +6. And the net charge of all of our anions is -3. So all of these cancel. Does that make sense? Yeah.
Do you have the lattice structure for this one?
Yeah, so the lattice structure for some of these gets pretty complicated. I don't have a picture of it. If you look online, there might be some available. But when you've got charges that don't necessarily match +1, -1, you get into more elaborate crystal structures. Yeah. All right. Does that make more sense, though, seeing it pictorially? Okay. The other important note, too, is oftentimes I see students where they write N2, Mg3. Conventionally, chemists like to always show their cations first and then their anions second. So let's make a note of that. Note, cations come before anions. It's just conventionally how all chemists worldwide will write out an ionic compound. All right, let's do another one. Let's do magnesium plus sulfur. So let's try this one and then check with your neighbor and see if you agree. All right, who feels confident with this one? A few people? All right, let's try this as a class. So we've got magnesium. Magnesium is what charge as an ion? 2+, right? It's in group 2A. So we'd say magnesium 2+. And then we've got sulfur. What charge is sulfur as an ion? -2. All right, so now if we try to do the flip-flop, we'd say, all right, let's flip-flop this. We would say, all right, there's Mg2, S2. Do you think this is the best way to represent this? Yeah, I would just switch this to MgS, right? We want to go with our least common denominator. It's already canceling out, so we know it's in a 1-to-1 ratio. So instead of showing it this way, you'd say MgS because we know it's a 1-to-1 ratio. So my second note is keep it simple. And that means go with the simple ratio. It just makes it a lot easier to look at. For example, I wouldn't write Mg2000, S2000. It's still a 1-to-1 ratio. All right, make sense so far? All right, so now we got to jump into naming. I know it's not the most fun, but we got to do it. We're going to go over naming ionic compounds, which in many ways are simpler than covalent compounds, but in other ways more complicated. And that has to do with there being two types of naming systems. So there's two types of ionic naming. The first type is whenever you have a group 1A or 2A cation. Those ones are really easy to name. And then the harder one is when you have a transition metal cation. Why do you think it's harder with the transition metal cation than a group 1A or 2A cation? Going back to that table, I said we can't predict the charge readily, right? So it's a lot harder to know what the charge is for a transition metal cation than group 1A or 2A, which are always going to be +1 and +2. All right, so let's start off with the easy one. We'll do group 1A and 2A naming first. Really anything that's not a transition metal will fall into this class. And I'll show you the simple naming convention. The simple naming convention is you start out with your cation. Cations always come first. So just name your cation, and then you have a space, and then you have anion second with an IDE suffix. All right, the important note is we don't use mono, di, tri, tetra. With ionic compounds, I'm going to abbreviate compounds. So no mono, di, tri, tetra, etc. All right, so let's try to practice a few of these. So first one I want to do is an ionic compound between, let's see, potassium and oxygen. So first thing I would do is determine the formula, and then we'll try to figure out the name after we're done with the formula. All right, so we've got potassium. What charge does potassium always have? It's in group 1, so it'll be 1 plus. Oxygen is in group 6A, so it would rather gain 2 electrons to get its octet. Just like we do before, I'm going to flip-flop these numbers. So it's going to be K2O. So this would be the formula. Now we have to figure out its name. We always list its cation first. So the name is pretty simple. It's going to be potassium. The anion is oxygen, but we need to have an IDE suffix. So what do you think would sound most appropriate? Oxide. So potassium oxide. Pretty easy to do this. We don't say dipotassium monoxide. We don't use prefixes with ionic compounds because we already know that it's potassium and oxygen, therefore it must be in this specific ratio to have charges cancel. So we just don't bother with mono, di, tri, tetra. All right, let's try a few more. All right, so for these, I'll have the formula on one side. And then the name on the other. First one we'll do Ca3N2. Next one we'll go from name to formula. And I'll do calcium sulfide. And I'll give you a minute to work on those. So figure out what the name would be here and what the formula would be over here. Yeah.
Maybe move the periodic table onto that board for this class period.
I could ask.
Flips, right?
My guess is they might say no. I don't know if there's nails up here, but I could see. Yeah. Would it be helpful if I brought the laminated ones?
Oh, yes.
Okay, I'll bring the laminated ones from now on because I know it's nice having a quick reference without having to look over 10 people. Yeah. All right, let's try to do this together. So first one, we've got 3 calciums. We don't use the prefixes, we just stick with calcium, right? We know it's ionic because it's between a metal and a non-metal. Okay, so this would just start out with calcium. And we've got nitrogen as our anion, and we want an IDE suffix, so what would we call this? Calcium nitride. So the key thing to remember is swap out that suffix to an IDE suffix that indicates that it's ionic. All right, calcium sulfide's a bit harder though. So let's try to break it apart. We know we've got calcium, which has normally what charge? So group 2, so it'd be 2 plus. Sulfur is in group 6A, so it would be 2 negative. So it looks like it's already canceling out. We don't need to worry about it too much. Instead, we would just say, all right, this must just be CaS. Make sense? So that would be calcium sulfide. All right, so now we've got to jump into transition metal naming. Group 1A and 2A is pretty straightforward though. All right, so let's stick with the naming convention and then I'll show you examples. Just like before, you always list your cation first, and then you have a Roman numeral, then you have a space, and then you have your anion with an IDE suffix. So the Roman numeral in this case is required for a transition metal to indicate what charge it has because they can vary a lot. How many of you remember all your Roman numerals? A few people? All right, let's review them really quick, just because I know they're not commonly used anymore. So we'll go up to 6. We typically won't deal with charges greater than that. All right, Roman numeral for 1 looks like an I. Roman numeral for 2 is 2 columns like that. Roman numeral 3 is 3 columns. Pretty easy to remember 1, 2, and 3. 4 is where it gets tricky. Who remembers what 4 is? IV. 5 is V. And then 6 is VI. You do the 1 after the V for 6. So remember these basic Roman numeral rules. And let's say I'm given a compound, and the formula listed on the bottle is FeCl3. We immediately know that it's 1 iron for every 3 chlorines, but we don't necessarily know the charge of iron right away. But we can figure it out. So we'd say, all right, iron has some charge. We know it's a cation, though. It's listed first. And then we've got 3 chlorine atoms. What charge does chlorine have when it's an anion? Be -1. It's in group 7, 7A, so it's a lot easier to gain 1 electron to become an octet. So this would be 1 negative, 1 negative, 1 negative. So what charge must the iron have in order to cancel out the chlorines? Well, it's got to be 3 positive, right? So we'd say must be 3 plus in order to cancel. All right, so now what we would do is work on the name. So we would say cation first is iron. Whoop, if I can spell iron. And the Roman numeral in this case is 3. So you do that in parentheses. So it'd be iron 3. And then the anion is chlorine with an IDE suffix, so it would be chloride. So like I said, this indicates that that iron has a positive 3 charge. So anytime you see a transition metal, you need to immediately think, I need to include a Roman numeral. It's easy to forget. All right, so let's take a look at a few examples, and I'll show you why this is really important. First example I have is CuBr. The second example I have is CuBr2. All right, so if we think about the first one, we've got copper. It's a transition metal. We don't know its charge immediately. And then we've got bromine as our anion. What charge does bromine have? It's in group 7, so it'd be -1. All right, so based on this, knowing that bromine's -1, our copper must be +1 to have it cancel. Okay, so we'd say must be +1. Okay, that means the name for this one would be copper Roman numeral 1. And then bromine is our anion, but we want an IDE suffix, so it'd be bromide. All right, versus the bottom one, we've got copper again with some unknown charge, but now we've got 2 bromines. We know bromine, when it's ionic, is always -1. All right, that means that the charge for this copper would be what? +2, exactly. Yep.
Would we ever write that, Roman numeral in the chemical formula to indicate which one it is?
So the question was, do you include the Roman numeral ever in the molecular formula? No. Essentially, they're assuming that you know how to cancel charges, so they just omit it. Yeah, good question though. Okay, so if we think about this one, this would be copper 2 bromide. So if we look at both of these, they look really similar. If I asked a chemist to hand me a bottle of copper bromide, they would say, which one, right? You have to have the Roman numeral to know which of these compounds you're talking about. Saying copper bromide without the Roman numeral is completely ambiguous. You have no idea if they're referring to copper 1 bromide or copper 2 bromide. So different cations in both of those. Does that make more sense? Roman numerals are tricky. It's easy to forget them, so always slow down on exams in particular, and just double check that you're identifying the transition metals. If you see a transition metal, immediately think, I need a Roman numeral here. All right, I think before we jump into polyatomic ions, oh man, how about this? Rather than jumping into a new section, I'll let you get a jump start on your problem of the day that's due tomorrow. So if you want to partner up, you can utilize these last 10 minutes to work on your problem of the day.